Hi, my name is Alex Reed, and I'm the sub-team lead for the Chassis and Drivetrain sub-team for the MSOE NASA RMC team.
Hello, my name is Noah Kennedy. I'm the Control Systems Lead for the MSOE NASA RMC team.
I'm Tim Buckman. I'm the Vice President of the CS team.
I'm Joseph McClanahan. I'm the Electrical Sub-Team Lead.
I'm Justin. I'm the Material Handling Sub-Team Lead.
And we're the MSOE Space Raiders. So about 2 years ago, we decided to revamp our team structure. Before this point, we were only a senior design team, which had a main focus on making not competition-ready robots, but robots that could function really well in one specific task or another. As of 2 years ago, we decided to make ourselves a club team, which means anyone from a freshman to a senior could join the team and put their hands on the robot. As you can see in the photo, we have a 26-person team, and we have a majority of underclassmen students. And a lot of these students have experience with robotics or other engineering in terms of internships or high school robotics or other work experience.
This year's robot includes some safety features, the most important of which is the kill button. This button uses a relay to cut off all power to the robot if for some reason it went haywire. There were also fuses implemented to protect the sensitive electronics should there be a power surge in the robot, as well as an ammeter that monitors the system for surges to protect the digging system in case of a jam. The electrical box is also going to be ventilated to prevent overheating.
So many of our the goals of the robot were specified by NASA as part of the competition, but some of the objectives we set for ourselves. From the list, the only ones that we set for ourselves was the budget, because we had limited funding, because we're a fairly new team, and being able to have it modular for disassembly and redesign. All of the rest of them were set by NASA for the competition, and for some of them we're disqualified if we don't meet them, and for other ones we lose points if we don't do as well in those areas. So this year, we'll touch on this more later, but we made a whole new design. Last year we went with a trencher system, whereas this year we did a bucket ladder system. So first we had to completely redesign the mechanical side of it, keeping in mind the electrical and controlling aspects of it. So like some of our motors were not allowed right off the bat because they drew too much power or were unable to be controlled. So that's kind of how we designed it. We designed it with the whole system in mind, and then designed individual pieces based on that.
So for our alternative analysis, basically we used a whole bunch of analysis like minimum risk analysis, lowest costs, and improve the outcome from last year's competition. So through this, we came up with a whole bunch of budgeting tactics and a lot of analysis. And so our budgeting include power, money, and weight, so that we can keep a low power, low cost, and a low weight robot. As well as that, we did a lot of analysis, like circuitry analysis, FEA, finite element analysis, and CAD modeling to make sure that we stayed within our regulations of weight and size. And through this system, one of our examples too was coming up with a decision matrix for the material handling system. And through that, we had 3 different ideas come in. And those ideas were an auger, trencher, and a bucket ladder. And from those ideas, we rated them on a whole bunch of criteria. And those criteria narrowed it down to the trencher and the bucket ladder. And then as a team, we decided that we wanted to go with the bucket ladder for ease of manufacturing.
Our design methodology started with phase A, concept development, which was just the brainstorming and of course the decision matrices from that brainstorming. We had to create requirements and verification methods for the competition and from the team, so making sure that our robot adhered to both the NASA requirements as well as our own internal requirements, as my friend Tim touched upon earlier. Phase B, we moved on to the preliminary design, meaning the initial CAD models and the initial kind of drafting of what we thought would be a good robot design. So this meant digging analysis, modeling a general kind of bucket ladder design, and new tread designs and a new chassis design, making sure that everything kind of fit together sort of loosely in this preliminary design stage. Moving on to our final design, this was our critical design review time, where we made sure that all of the designs were final, all of the materials we were using were final, as well as for the coding and wiring of the robot, making sure that everything sort of worked together. Troubleshooting code was really big during Phase C, making sure that all of the code that was designed to operate the robot worked correctly. And moving on from that, our final phase, Phase D, was experimentation, where we kind of made sure that the robot worked after it was built, making sure it drove, making sure it dug correctly, making sure it deposited material correctly. And through all this, we made our proof of life video showing NASA that our product might actually work. Final configuration and functionality. For mining and collection, we made sure that the bucket ladder was capable of collecting not just regolith, but icy regolith. And we made sure that our transferring system was capable of holding our desired amount and dumping that up and over into the collection bin that NASA gives us. For the chassis, we ensured that it was modular and structurally supportive for the mining and collection and drivetrain, making sure that the chassis held everything together. And for the drivetrain, making sure that the robot had enough torque to move the robot and that it was able to grip in the very sandy, dusty environment that NASA provides for us as a testing ground. For our electrical components, we made sure that a 200 amp starter relay was used in the kill switch for reliability, making sure that the kill switch did not fuse and making the kill switch inoperable. And we made sure that the e-box was sealed to prevent dust from entering and killing electrical components. And finally, for controls, we ensured a fly-by-wire control system and a web-based front end, which made sure that it was easy to use and that anyone that was driving the robot could see what was going on. And finally, we made sure that we had multiple onboard camera feeds so we could see what the robot is doing at any time.
So from last year to this year, we've had several comparisons of the similarities and improvements that we want to touch upon. And so for the 2017 year and 2018 competition, we had a trencher that collected some gravel. It was very low mass and low weight, and our transferring system that was only able to collect 1 kilogram of gravel or icy regolith, and it was also a very modular design. From last year to this year, we stuck with the bucket ladder shown in the little model, and from there we have a bucket system that can collect more gravel, transferring system that can hold more mass of the actual icy regolith that we're collecting. It's very low mass and has a successful drivetrain and more dust prevention systems for electronics and critical electrical components. And so what we have here now is we have our bucket ladder that gets actuated down and plunged into the ground. And in this video, we had it go all the way down below our table, which was equivalent to the ground, about 18 inches approximately. It was pushed down by 2 linear actuators, and through those linear actuators, the bucket ladder could be powered by a DC motor, which is attached onto our system now. These buckets spin, and they're driven by a belt, as shown in the robot right over there. And from there, we had 14 buckets attached, and they plunge into the ground, and they can collect gravel and sand from our testing. And they also include a very lightweight aluminum tubing system that was examined in finite element analysis. So the collection system now, we have a transferring bin that's made of polycarbonate plastic and transfers up through a linear actuator slide that's driven by 1 DC motor and a gearbox, and it tips over when you have a counterweight, and it can carry up to 10 kilograms for experimentation. And
moving on to the chassis now, made to connect critical components of the robot together. And through design and through CAD and finite element analysis, we designed the chassis to distribute load through the top and bottom crossbars in this sort of diamond shape to make sure that load is distributed evenly. The riveted gussets that we connected the robot's chassis pieces together with are easy to use and easy to manufacture, and the rivets are easy to drill out should something go wrong and you have to take out a chassis member. The aluminum stock material that we use for the frame members allows for strength in a lightweight package. Aluminum is a lot lighter than steel is, and for our uses, it can hold this near equal to the same amount of weight. And it's really cheaper as well. So simple aluminum square extrusion is inexpensive and it's really easy to work with, which is why we decided to go for it in our chassis. And moving on to the drivetrain, we decided to use hoverboard motors, which you might have seen a few years ago. They were very popular. They're power efficient, easy to mount, and they're really cost effective. We designed a variable height mounting system for them for use when we're testing the robot. We can mount it a little bit higher to make sure nothing kind of scrapes against the ground. But we also have an optimized height for during competition runs where it's lower than the 3/4 meter height restriction, and it allows for the deepest plunging depth for our bucket ladder. Finally, the drivetrain has 3D printed wheel covers with increased surface area, and because of the way that they were designed, they were easy to change during our Phase B kind of design process. And so with that, they're also easy to change should testing occur during Phase C and D that might break a wheel, and we determined that it was the cause of the 3D printing, and we can change the design, go back and make it better and print it again. And easy to repair in case of critical failure. We can easily 3D print a new wheel to go over, versus if we use different materials such as sheet metal or a different material, it might take a week or two to get a new wheel cover, versus here we can just 3D print it and have it in a matter of a day or two.
For the electrical subsystem, we decided on using 4 cobalt 24 volt 4 amp hour true batteries. We tested these to be able to output at least 15 amps continuously each. With 4 of these combined, it far exceeded our current requirements. So we were able to meet that, and the robot was able to run for over 20 minutes. We also implemented the kill switch using the 200 amp starter relay. We initially used a 40 amp relay, but with the current spike, it wound up fusing it, and the kill switch no longer worked. So we decided to go with the starter relay, which can handle the current surges and still be functional. The E-box is also going to be sealed with silicone to prevent dust from getting in.
For the software aspects of the control system, we made use of a fly-by-wire control system where commands from the robot operator are validated to make sure that they're safe to perform at the current moment. We do this by having only one subsystem that's allowed to be active at a time. So the user cannot attempt to the user can only attempt to run one of the drivetrain, the dumper, or the digger at the same time, because we could draw too much power from the electrical system if multiple were to be run at the same time. So the operator has to toggle between the different subsystems, and the other 2 subsystems are disabled. So we also have multiple camera feeds on board the robot, where the operator can switch between the different feeds, but they cannot view multiple feeds at once. This was done in order to conserve bandwidth, as having multiple feeds would require intense compression, in order to meet the bandwidth requirements, at which point having multiple feeds would become unimportant anyways, as the operator would not be able to make use of that information due to the low detail. The control system was also designed to be extremely modular, so all of the different software for the different subsystems were fully decoupled and were actually thread segregated. So if a physical change was made to the robot, it would require minimal code changes, because only the code for that module would be affected.
So budget management is very important in any team, especially a team like ours, which is smaller and has a smaller budget. So with a budget of $5,000, we split it across the subsystems based on what we anticipated their needs to be. We did this by having them pick out parts that they might use just as an example, so that we could compare the costs of the different subsystems. So that all that information is in the chart. We did this all using Excel. As you can see, some of the predicted numbers aren't actually the same as what was actually used, but we did our best. The time schedule, so we began with a new design in fall of this year, and then we were building it and then wiring it and coding it. This spring, we decided to switch to a 2-year program instead, so that we could have a fully built mechanical robot at the start of the fall, which would give the controls and electrical sub-team something to work on right off the bat. and would give them enough time to fully code and wire it and test it as much as they wanted to. The team structure is pretty much the same as any team. The president's on top, and then the president with the vice president and the e-board are right under that, and then the subsystem leads with the individual subsystems. This year we have 4 subsystems compared to last year where we had 3. We split up controls and electrical subsystems so that we could hit the electrical components more effectively and have more time with them.
So we evaluated the risks of our different components based off of a risk matrix. Luckily, we only identified one extreme risk from this process, which had to do with the control board that we make use of on the robot. The BeagleBone Black that we make use of has known bugs with its firmware, and we've identified that extreme risk, and we'll be moving to a different board that doesn't have some of the issues that one has in the future. So some other sponsors for the team, we've got NASA and MSOE. In addition, we also have sponsorship from the Wisconsin Space Grant Consortium, Brady, Ditch Witch, Komatsu, IGUS, and Manitou. So, you guys have any feedback or questions for us? Please feel free to email us back and let us know. So, for references, you can feel free to check the NASA rules and rubrics, or to look at our systems engineering paper. We also have a YouTube channel with a lot of videos of our different components in action.
We'll provide those videos with this email, the presentation.